Let's solve lots of multiple choice questions for A-level physics. In this video, I'm going to solve as many questions as I possibly can. You can use the chapters to navigate to your exam board and the topic of the particular question. We're going to start off with the OCR specimen paper. So this is paper 2. Question 1, to find the density of the wire, a student makes the following measurements. The equation for M, etc. is used. What is the percentage uncertainty in the answer? Okay, so we're going to need to add the percentage uncertainties because we are multiplying and dividing quantities. What is the percentage uncertainty going to be in the mass? The way I always write this is right over left times 100. So I'm going to write 0.02 over 4.00. I'm going to multiply by 100 at the very end, plus, okay, what else has an uncertainty? Pi doesn't have an uncertainty. Now d squared, because it is squared, I'm going to multiply the percentage uncertainty in the diameter twice, so multiplied by 0.05, divide that by 250, and then finally we have the length. So the length plus, so this is equal to 0.055, but then it's not really a percentage yet. We need to multiply the final answer by 100, which is going to give me 5.5%. Correct answer is D. Okay, next one. A copper wire is connected across the cell. The conducting electrons within the copper wire move. Which statement is correct about these electrons? They drift towards the negative end of the cell. This is not true. They're going to drift towards the positive end. They have random speeds because of collisions with other electrons. This one is a little bit debatable. The speed is well, the drift velocity is not random. It's different compared to the speed of a molecule in a gas, for instance. They travel for the wire the speed of light. That is not correct. They collide with the vibrating copper ions. This one here is definitely correct, and those collisions are the heart of what we call resistance. Okay, question 3. We have a resistor. And then we have this cell across here. This is an internal resistance question. So immediately I'm going to write that E is equal to V plus IR. So what are we given? The voltmeter reading is 9 and the ammeter reading is 0 when the switch is open. So this here will just be our EMF. That's going to be 0. Our terminal PD is going to be 6 and plus the ammeter reading, which is just 2. So what we're going to get is that 3 is equal to 2R. R will be 1.5 ohms. Correct answer is A. Okay, next one, question 4. Which of the following statements is true about photons? So all photons travel at the same speed in a vacuum. So this is correct. All photons travel at the speed of light in a vacuum. Photons have no charge. This is absolutely true. Otherwise, if it did have charge, things would get charged up as light was falling onto them. Anyways, different story. The energy of a photon depends only on its frequency. Well, this one here is also true. The energy of a photon is equal to hf, where h is just a constant rather than a variable. So 1, 2, and 3 are correct. Okay, question 5. The electrons travel through a thin layer of the polycrystalline metal and they're diffracted. Which statement is correct about these electrons? The electrons travel as photons through the metal. That's not correct. The electrons have a wavelength of about 10 to the power of minus 10. Well, 10 to the power of minus 10 is roughly the atomic spacing, so this is a good contender for the correct answer. But let's have a look at the rest of it. The electrons are diffracted by holes in the metal. Well, they're diffracted by the molecular structure. I guess this here depends on the definition of what a hole actually is. I think they mean more of a macroscopic one, like a microscopic opening, but I'm going to go that this is probably incorrect. The electrons repel each other to produce the diffraction. That one here is rubbish. The correct answer is B. Okay, question 6. We have a sodium lamp that is rated at 40 watts and 12% of the power is emitted as light of certain wavelengths. How many photons of yellow light are emitted per second? The first thing that we're going to say is that the number of photons is equal to the total energy divided by the energy of an individual photon. Okay, so the total energy is just going to be equal to 12% of the power, 0.12, multiplied by the time, whereas the energy of an individual photon is just hf, which is just hc over lambda. Now we're ready to plug in some numbers, so it's going to be 0.12 multiplied by the power, which is 40, multiplied by the time, which is per second, so it's going to be times 1. Now let's divide that by Planck's constant, 6.63 times 10 to the power of minus 34, and multiply that by the speed of light, 3.0 times 10 to the power of 8, and then divide that by 5.9 times 10 to the minus 7, or in brackets. This thing here is still underneath the fraction. Okay, let's see what we get. We're going to get around 1.42 times 10 to the power of 19. Quick mental check in the end. This is a large number and it is probably correct. Okay, next one, question 7. We've got a DC supply is used to charge a 12-volt car battery of internal resistance 0.8 for 6 hours. The current in the circuit is 2.5 amps. How much electrical energy is provided by the charging supply? Okay, so how are we going to tackle this? So I think this question here has a trick, because we're getting 14 volts at 2.5 amps. Some of it goes into the charging, some of it is kind of essentially lost through this internal resistor. But overall, the total energy that's been supplied is just VIT, which is going to be 14 times 2.5. The time is in hours, so it's going to be 6. Convert that to seconds, 3,600. And this here is going to give me 756,000. Correct answer is D. Okay, next one. The electric potential is minus 1.2 times 10 to the minus 4 joules per coulomb at a point 1.2 times 10 to the power of minus 5 from an isolated electron. Okay, so let's do a drawing. Here is my electron, and here is this distance, which is 1.2 times 10 to the power of minus 5 meters. The electric potential here is this value, minus 4 joules per coulomb. Okay, an alpha particle passes through this point. So we put a alpha particle right at this point. What is the magnitude of the electric potential at the midpoint between the alpha particle and the electron at this instant? This is a really good question. So it'll be tempting to go into long calculations, but let's just split it into two. So what I'm going to say is, imagine if suddenly right over here you didn't have an alpha particle, but you had just a proton. So actually, even simpler, let's just imagine that we simply have the electron. because the equation for potential Q over 4 pi epsilon naught R, if R decreases by a factor of 2, the magnitude of the number of V will increase by a factor of 2. So just due to the electron, the potential, let me just do a better diagram. So this here is the distance 1.2 times 10 to the power of minus 5. Let's get rid of my kind of clunky diagram over here. So the potential here, just due to the electron, is minus 1.2 times 10 to the power minus 5. So right over here, it will be even more negative. So it's going to be minus 2.4 times 10 to the power of minus 5. Now, what I want you guys to imagine is that I put a proton here. What will happen to this potential? Well, this potential will increase to 0. Now, what will happen if I was to place 2 protons? Well, if I place 2 protons, this thing here will increase to plus 2.4 times 10 to the power minus 4. But what has the same electrical charge as 2 protons? An alpha particle. It will be identical to this. Therefore, the correct answer has got to be B. Okay, let's have a look at the next one. We've got a coil with 3 turns of a wire is used in an experiment. The graph shows the variation of magnetic flux linkage with time. What is the EMF induced across the ends of the coil? Okay, so EMF is the negative of the rate of change of flux linkage. This will make the gradient of the graph equal to the EMF. We're just going to need to be careful of the units. So they quite like giving us non-standard units. You can see milliseconds here, and you can see Webers, 10 to the power of minus 4 Webers here. So working out the gradient, we're going to see that this is equal to 0.4. Just a reminder that the EMF is equal to the negative gradient. Also, make sure to take really large gradient triangles in the actual exam. So this here will correspond to the correct answer being C. Okay, the next question, we have a graph of binding energy per nucleon, which is shown. This question here actually has a trick. Which nucleus has the largest magnitude of the binding energy? So notice how it's asking us for the binding energy rather than the binding energy per nucleon. So the largest binding energy is actually D, because D actually has a ton of nucleons. So something like, I don't know, uranium 238, there's 238 of them. Whereas this is a graph of binding energy per nucleon. The peak here is iron. So iron has only 56 nucleons, I believe. So there's a large difference in the actual total binding energy, because this one here is multiplied by 238. Okay, question 11. Okay, question 11. We have a radiographer in a hospital directs a parallel beam of X-rays at the leg bone of a patient. We've got the attenuation and absorption coefficient of the bone is 0.7 centimeters. Okay, so the equation we're going to use here is that I is equal to I naught e to the minus mu x, where x is the thickness and mu is the absorption coefficient. So what is the percentage of X-rays transmitted? So I over I naught is, let's be consistent here with the i's and the way we write them, is equal to e to the power of minus mu x. So this here is essentially the ratio that we're looking for. Well, this thing here will just be equal to e to the minus 0.7 centimeters multiplied by 0.7 per centimeter, so it doesn't really matter what the units are here, because centimeters to the power -1 will cancel out with centimeters. So what are we going to get? Let's plug this thing into our trusty calculator, and we're going to get that I over I naught is around 0.61, which is around 61%. Closest answer seems to be D. Okay, cool. Next one, when a nucleus of uranium-238 absorbs a neutron, one combination of fission products can be tin-126 and a nucleus of element X. 13 neutrons are also emitted. How many neutrons are there in the nucleus of element X? Which sounds pretty cool. Okay, well, we just need to add them up. So the numbers on the left have to add up to the numbers on the right. So we have a total of 239 nucleons. Are we looking for the nucleons? Let's have a look. How many neutrons? Okay, so we're just going to be looking for the neutrons themselves. So we're going to need to find the proton number and then the nucleon number and then take them away. So we have 126 plus 1 on the right hand side, so that's those two add up to almost a mistake, plus 1 times 13, because there's 13 neutrons, so that's 126 plus 1 times 13. That's going to give me 139 nucleons without element X. So 239 take away 139, well, this here will just be equal to 100. Okay, so the total proton number is 92 on the left. Proton number here is 50, so this means that we're going to have 92 take away 50, which is just 42, which is the... Don't be tempted though, 42 is not the answer to everything in the universe. Remember, this question was asking us about the neutron number, so it's going to be 100, take away 42, which is 58. Correct answer is C. Okay, next one, potential difference across the cathode and the anode of an X-ray tube is V. The minimum wavelength of the X-ray photons from the tube is lambda naught. Which of the following statements is correct? Okay, so EV is equal to HC over lambda in general. So if lambda naught is halved when V is doubled, so they seem to be inversely proportional to one another. Yep, so this seems fine. Lambda naught is unchanged when the temperature of the cathode is increased. So I'm gonna go with yes. The temperature of the cathode is heated up by voltage. I believe this is also a separate voltage actually. If you've worked with an X-ray tube, do let me know down in the comments. This question is a little bit confusing, but you typically don't have that high of a voltage to actually release the electrons, but the voltage is really the potential difference between the cathode and the anode when you connect them. That really accelerates the electrons to a really high speed. Now, it is also independent of the material of the cathode, so I guess electrons are going to be emitted, and the speed of these electrons will depend on the voltage in particular that's accelerating them rather than what's actually emitted them. So this here also seems true. Correct answer should be A, I think, 1, 2, and 3. Okay, question 14. 2 leptons are emitted when a down quark decays into an up quark. So which of the following is correct? In terms of the force that's responsible, anytime we have a flavor change of a quark, we need to be dealing with the weak nuclear force. I also call it the chameleon force as well. I think the Fermilab channel also calls that the chameleon force. I really like that. Okay, anyways, so weak nuclear force. So when a down quark turns into an up quark. So this happens when a neutron turns into a proton, because that's DDU, that turns into a UUD. Now, when a neutron turns into a proton, let me just write that properly here. When a neutron turns into a proton, charge needs to be conserved. So this is 1, 0. We have 1, 1. So we are going to need to have an electron like that, plus an anti-neutrino. A good way of remembering this, if I can see the dash here, then I know that there's a dash here, it's an anti-particle. And remember, neutron is DDU, that turns to a UUD. Electron and anti-neutrino, weak nuclear force. Correct answer is D. Okay, question 15. A right loop of insulated wire is in a uniform magnetic flux density 18 milliteslas, and we have quite a lot of information here and quite a lot of values. What is the magnitude of the force experienced by 1 centimeter of the section of this loop? There's a trick. If we were to zoom in right over here, we're going to see that part of the wire goes this way, part of the wire goes the other way. And if that is the case, well, they should be experiencing force due to F is equal to Bill, but because the current is in opposite directions, by 1 centimeter section of the loop, I mean sort of, I guess, of the entire loop. So therefore, they're going to experience directions of the force, same force in opposite directions. So the magnitude of the resultant force should be 0 newtons. Okay, hopefully this was useful. Let's do some more from a different exam board. Now, let's do some AQA questions. I'm not really allowed to show you the actual paper, so you need to have a look at your copies. This is paper 2 from these sample papers, and these are not official solutions in any way. There could be mistakes. In fact, do let me know if you spot a better way of doing a problem. Okay, so let's have a look at question 7. So question 7 was asking us for the correct unit of this quantity g squared divided by g. So we've got a few options over here. They're all in terms of newtons and other quantities. So first of all, what is the unit at the top? Because g is equal to the weight divided by the mass, so the unit will just be newtons per kilogram for g. What about for uppercase g? Well, remember, from Newton's law, F is equal to gmm over r squared. Therefore, g will be fr squared over mm. Okay, so this means that g will be newtons meters squared over kilograms times kilograms is kilograms squared. So g squared divided by g, what is that going to give me? Newton squared kg to the power of -2, and then we're going to divide this by this, which is newtons multiplied by meters squared kg to the power of -2. We can just get rid of the kilograms like that. So what are we going to be left with? Newtons. Hang on, let's try it again. Newtons at the top, and then m to m squared. So this here means the correct answer on that paper was D. Okay, so question 8, we've got a planet that has radius which is half the Earth's radius, and so the radius has decreased by a factor of 2, and the mass, which is a quarter of the Earth's mass. Okay, so what is the approximate gravitational field strength? Well, because G is equal to Gm over R squared, if the mass has decreased by a factor of 4, this will decrease G by a factor of 4. If R squared, if R decreases by a factor of 2, R squared will also decrease by a factor of 2 squared, which is also 4, and this will increase G back up by a factor of 4. Therefore, G will be unchanged, so it's going to be approximately 10 newtons per kilogram, meaning that the correct answer is C. Okay, so question 9 is really interesting. We have a mass M that is pretty close to another mass, which is 4m. So the distance between them is actually d. The resultant gravitational field strength is 0 somewhere along this line. So the options, well, actually it's going to be 0 somewhere along here, and it says that y is the distance from the center of mass m to that point here. So this here is y, and the important thing is that right over here the resultant gravitational strength is 0. Now, why is this point further away from the midpoint? If it was at the midpoint, that will only be true if the two masses are equal. Okay, but they're not equal. This one here is quite a bit larger, the actual mass, so the distance will be somewhere beyond the midpoint. Because of that, we can immediately find out the correct answer. The question is actually asking us the ratio about y over d. So y has to be a pretty small fraction of d. It has to be beyond the halfway point. So the only option that allows this is actually B. So what were the options? A was a half in this question. That's not true. It will only be true if the masses were exactly the same. B, a third. Yep, certainly possible. C, 2/3. Well, no, because if it's 2/3, that would mean that it's going to be beyond the halfway point, so this is absolutely impossible. D, 3/4, this is also impossible. Now, you can also do this question in terms of a calculation. I'm going to leave the calculation to this question here, d over 3. However, this is pretty unnecessary because just by the process of elimination, we can work. Okay, so question 10, this is finally a nice and easy question. Which of the following statements about Newton's law of gravitation is actually correct? So the correct answer is D, how various factors affect the gravitational force. Why is that? Because F is equal to Gmm over R squared. This is Newton's law of gravitation about the gravitational force. The factors that affect it are the mass of the two particles/objects, and r is the distance between their center of masses. Okay, so question 11 is really interesting. We have the following situation. We've got essentially a radial field. Let's draw it kind of properly. So something like this, then like that. Then kind of horizontal, then kind of a repeat. This is not an exact drawing, by the way, guys. Then a little bit like that. Okay, so the field direction is given to be going this way. So field lines, electric field lines, always flow from positive to negative. Because they're radial, this means that somewhere over here there is a negative charge. Okay, so we have a negative ion which is placed somewhere along. We've got an equipotential line across here, and somewhere around here we've got a negative ion. So negative ion. Which of the following statements is true when the charge is displaced? So the correct one is that along the line PQ, which is right over here, the magnitude of the electric force on it will be unchanged. So it's going to experience a force, and that force will be exactly the same along essentially the line of symmetry, because the distance F is equal to KQQ over R squared will remain exactly the same, assuming this is a perfect radial line. Now, why are the other options not true? A says to the left the magnitude of the electric force on it decreases. No, the opposite. If I was to take this and bring it over here, the force will increase. To the right, potential energy increases. Wrong, potential energy will decrease if I move it away. So kind of like if they're really, really close together, because they're both negative, they're going to have the potential to get released, and this is why the statement is not true. Along the line PQ towards Q, its potential energy decreases. Once again, this is also not true. The potential energy will remain the same along this equipotential line. So therefore, the only correct statement is D, that the force is constant along this line PQ. Okay, so for question 12, we've got two parallel plates like that, some charge, and then this distance here is d over 2, this distance here is d over 2. We've got a charge somewhere here. Which expression gives the magnitude of the electrostatic force? Well, F is equal to EQ, and E is just equal to voltage over the distance, but the total distance is just going to be D. This is going to be V d multiplied by q, and this means that the correct answer has got to be B. Question 13, we've got an alpha particle like that, and that's going to be deflected by a nucleus. We've got some sort of position P with the nucleus being here. Which of the following statements is correct? Well, the correct one is that the speed is least at P. Why is that? Because at that point you have the maximum conversion of electrostatic potential energy to you have the maximum conversion of kinetic energy to electrostatic potential energy. So at that point Ke is a minimum and potential energy is a maximum. So for question 14, we have a positive charge, and then a distance r away from it we have a potential of 45 volts. So if we were to decrease the distance by 1.5 meters, the potential will increase to 50 volts, and what we need to do is figure out the value of R. So what is the best way to tackle this problem? Multiple different ways. I prefer just doing that numerically in a way, in other words, writing out some equations. So what I'm going to say is that the potential is equal to the constant multiplied by the charge divided by R. So when this is R, V is 45. Now, this of course means that KQ will be equal to 45 multiplied by R. Okay, so if that's the case, let's figure out the equation for here. We know that this will be 50 when we have a distance of R minus 1.5. But we already have the value of the constant multiplied by Q. So what I'm going to say is that 50 is equal to 45R over R, take away 1.5. Okay, so then we're going to say 50R take away 1.5 is equal to 45R. Okay, so we get 50R take away 50 times 1.5 is equal to 45R. Okay, let's bring all the R's on one side. So we're going to get 50R take away 45R. In other words, this will be just 5R, and this will be equal to 50 times 1.5. And then we can cancel out this. So R will just be 10 times 1.5, which is just 15 meters. Now this will correspond to the correct answer being D. So for question 15, we've got a couple of charges, plus Q and then minus 2Q with a distance D between them. Okay, so if that's the case, we can say that there's going to be an attractive force with a magnitude of minus 2Q multiplied by Q over 4 pi epsilon naught D squared. So what are the changes that are made to the actual system? Each particle is then given an additional charge of plus Q. So this would mean that this left charge will now be 2Q, and the other one will just be minus Q, because minus 2Q plus Q is just minus Q. And what's happening to the distance? The distance increased to 2D. This is not drawn up to scale. Okay, well, the force, the numerator of the fraction will actually be exactly the same, because we're just going to get minus Q multiplied by 2Q, which is exactly the same as what we had before. Divide that by the distance, divide that by 4 pi epsilon naught. Now the distance, because it's squared, will give me an increase of a factor of 4, because 2 squared is just actually equal to 4. If the distance increases by that factor, the force will decrease by that factor. And this is precisely why the correct answer is A. The force is attractive because A, it's negative, and we also have a positive charge and a negative charge, so they will attract one another, but then it will decrease by that factor. Okay, so question 16. Which of the following statements about a parallel plate capacitor is incorrect? So if we look at C, it says that the charge stored in the capacitor is inversely proportional to the PD across it. Well, this is incorrect because charge is equal to CV. Therefore, Q being inversely proportional to V is not correct. So, therefore, correct answer is C. Okay, so for question 17, we're given quite a lot of data. So V0 is equal to 6 volts for a capacitor that's actually discharging. So, now, what would the potential difference be after time, which is equal to the time constant? So what is the time constant? Time constant is given by CR, and this is the time at which the voltage will drop to around 37% of its initial value. Okay, so the time constant will then be just given by 10 millifarads, 10 times 10 to the power minus 3 multiplied by 500. And this is just going to give me 5 seconds. Okay, so if we have 10,000 readings in 10 seconds, then we're definitely going to get half of that. Oh, we should say 1,000 is given as 1,000 in the question, my bad. So definitely we are going to have 500 readings in 5 seconds, and the time constant is just equal to 5. Okay, so after that, we can work out the voltage. So the easy way is to remember that at time is equal to the time constant, the voltage drops to 37% of its initial value. So 37% or 0.37 of the initial voltage, which is 6, is going to give me pretty close to 2.2 volts. Therefore, the correct answer is D, 500 readings, 2.2 volts. Question 18, fairly standard experiment, but we have a wire which is floating in a magnetic field. So the word floating means that the magnetic force is going to be balancing the gravitational weight, mg. So we're going to get Bill is equal to mg. Then we can just simply rearrange for m, and we're going to get that m will be equal to Bill divided by g. We can plug in all the numbers. So the in the question, the B field is 5 times 10 to the power minus 2 Tesla multiplied by the current, which is 2, multiplied by the length, which is 0.3. Always be careful with the units here. So far, I don't see any non-standard units, divided by G 9.81. And we are going to get around 3.05 times by 10 to the power of minus 3 kilograms. That corresponds to correct answer being B. Okay, so moving on to question 19. It's about charged particle moving at a constant speed in a circle. Anytime we come across this in a question, just write down QVB is equal to mv squared divided by r, setting the magnetic force on the charge to be the net centripetal force. Okay, so the velocity is going to cancel out. I want to find the frequency. Okay, so I'm going to say that QB is equal to M, V is equal to omega R divided by R. The R's are going to cancel. So then what we're going to get is that QB is equal to mass multiplied by omega, which is 2 pi f, meaning that the frequency will just be given by QB divided by 2 pi m, and this here will correspond to correct answer being A. Okay, question 20. We have a rod that's being moved in a magnetic field. So this here is my magnetic field lines, and this here is the rod. Okay, the only way we're going to get an induction is if the surface area cuts through. So this here is a side view. So the field lines have to be parallel to the normal in order to get a change of magnetic flux linkage. So we have to move the rod either this way or this way. So the direction of motion will be horizontal in order for an EMF to be actually induced. Okay. Well, what will the actual expression for the EMF be? Well, from Faraday's law, the induced EMF is equal to the rate of change of magnetic flux linkage, delta T. Well, this here is just going to then be equal to delta NBA cos theta. Now in this case theta is 0 because the normal is just going to be parallel, so we can ignore the cosine term with a little minus sign here, delta T. Okay, so what we can say then is that out of all of these, well actually let's express the area as a multiple of 2 dimensions. One will be just the length of the rod, and then the other one will just be how much it has traveled divided by T. Out of those quantities, the only thing that is actually changing is x and t. So we're going to get NBL x over t, which is just actually the speed. So we are just going to get the magnetic flux linkage. In this case, n is just equal to 1, isn't it? So I'm going to write this over here. This is just a general case. So we should get minus BLV. The magnitude of it, depending on which way we're moving this, it would either be a plus or a minus. The magnitude will be BLV. Therefore, the correct answer should be B. Okay, for question 21, I am pretty convinced there is a mistake in the mark scheme. Why is that? So for a simple pendulum, the time period is given by 2 pi root L over G. This means, of course, the frequency is just going to be the inverse of that, which is going to be what? 1 over 2 pi root G over L. So if G was to decrease, then the frequency will decrease. For a mass spring system, G does not appear in the equation whatsoever, so I'm going to go with my answer being D. It's possible the question may have had a typo as well. They may have meant to say that G potentially increases as you go down the line. That would lead to the correct answer being C. Okay, for question 22, we have a graph of flux linkage and phi against time. Now the graph looks something like this, and then there's a certain time t0, and then the graph is constant. Okay, so the induced EMF is the gradient of the graph. In fact, it's minus the gradient, minus the rate of change of magnetic flux linkage. So here it is constant, and then right over here the flux is not changing, and if the flux linkage is not changing, then there's no EMF, so the induced EMF is 0. This means that the correct answer has got to be C. Okay, question 23. So a liquid flows continuously through a chamber, and when a steady state is reached, the liquid leaves the chamber at a higher temperature than the liquid entering the chamber. Okay, the difference in temperature is delta T. Which of the following will increase delta T with no other change? Okay, so the main thing to notice is the change of temperature is determined by this equation. In this case, rather than delta theta, they've just called that delta T. But you can see that delta T is inversely proportional to the specific heat capacity. So delta T is equal to E over mc. So this means that if the specific heat capacity is lowered, then delta T will be increasing, the change of temperature will have to increase. Okay, so for question 24, we need to find a ratio of the specific heat capacity divided by the specific latent heat of fusion. Okay, so the temperature of a hot liquid in a container falls at a rate of 2 kelvins per minute. So this means that initial sentence tells me that delta theta is 2 Kelvin, and the amount of time over this happens is just 1 minute. Okay, so what I can do next is actually work out 2 separate equations to allow me to get this ratio of C divided by LF. Okay, so the specific heat capacity is just going to be equal to the energy required to just heat it up, to change the temperature by 2 Kelvin in 1 minute, over m delta theta. Well, this here should say theta rather than Q. Divide that by the specific latent heat, which is the ratio of the second energy, which is fusing it, the energy that's escaped really. Divide that by the mass. Okay, So energy is power times time, and the power will be the same. So power multiplied by time divided by the m's have cancelled out, delta theta. This here, the first time is going to be different to the second time because the first time was 2 Kelvin. Sorry, the first time was 1 minute. The second time in the question is 20 minutes. So right here at the bottom, we are going to get power times T2 divided by m, which is cancelled out already. So we are good to go. And the power will also cancel out because it's still on the same heater. Now my T1 is 1. So the top of the fraction is going to be 1 over delta theta, which is 1 over 2. And then we're also further dividing by 20 for T2. So we're going to get 1 over 40, meaning that the correct answer has to be A. So question 26, I really liked this one. The trick on this one is to consider that there is no change in temperature, therefore we have to use Boyle's law, which means that pressure times volume is equal to a constant. Now, after the valve is open, suddenly we're going to have 3V of volume available. The easiest way is just to ignore one of the containers first of all. So let's just say that we open up the valve and only this one here kind of expands through it to the other one. What will happen to the pressure? Well, pressure times volume is a constant, therefore P1 V1 will be P2 V2. So the initial pressure was P, the initial volume was 2V. However, now the new volume will be 3V, and we're going to have some new pressure, which is P2. If we rearrange for it, we're going to get that P2 is just P times 2 over 3. Let's do the same strategy for this one. Let's imagine that one of them is now just not in the picture. We just expand this container into the 3V volume. So applying Boyle's law, the initial pressure is 2P, the initial volume is V. Now the final volume is 3.2, and I've called the new pressure P2 prime. So rearranging for that, we're going to get that P2 prime is equal to 2/3 of the initial pressure. Finally, we just need to add the two pressures, and what we're going to get is 2 over 3P plus 2 over 3P. That's going to give me 4/3. Therefore, the correct answer is C. Okay, so question 27, we have a radioactive nucleus emits 2 beta minus particles. So in 2 beta minus particles, we're going to have 2 neutrons converted to 2 protons. So just that part of the reaction is going to gain us 2 different protons. But also we're going to emit an alpha particle. This means that we're going to lose 2 protons. Because of that, we know that our element will be the same because the proton number will be exactly the same. There will be an isotope though, because we will have lost 2 neutrons. Question 28, which of the following best describes the decay constant? Well, the correct answer is D, because this equation is true. A is lambda over n. That is the constant of proportionality which links the rate of decay A with the number of undecayed nuclei. A is the rate of decay. A good way of writing the activity is kind of like delta n divided by delta t. Another way to think about the decay constant is that it's the probability that a individual nucleus will decay per unit time. Okay, so for question 29, we need to have a look at the ratio between the radii of the following nuclei. So the formula that gives the radius of a nucleus is right over here. R0 is just a constant, and what we're going to do is we're going to do the atomic mass number, which is just 125 raised to a power of a third, divide that by 64. 4 raised to the power of a third, and this here will give me 5/4, which is 1.25. Correct answer is B. Okay, so for question 30, we have a substance that's radioactive, and after 64 days, the activity has fallen to 1/16 of the original activity. The question is, how many times has it halved? So after 1 half-life, it will fall to half the value. After 2, we're going to have 1/4, then 1/8, and then 1/16. So how many half-lives is this? 1, 2, 3, that's 4 half-lives. That whole process took 64 days, so 64 divided by 4 means that the half-life has got to be 16 days. Correct answer should be D. Okay, so for question 31, there is a bit of a trick to it. We have the graph of the binding energy per nucleon, so that's binding energy per nucleon. Okay, and then we have an element somewhere over here with kind of like the typical graph, kind of looks something like this. And if I was to go kind of across the axis, I got sort of around 8.2 mega electron volts. It's not a super accurate measurement. In the exam, I would use a ruler and do that properly, but also we can see that the answers are pretty far apart, so it's going to give me a good idea of what the good answer is. However, this here is for element 1, for an element with 180 nucleons, so 184, excuse me. So the element that we want to find the binding energy of has 184 nucleons, 74. Because this number here is 184, and each of those nucleons is going to have 8.2 mega electron volts of binding energy. So the total binding energy will be 184 multiplied by 8.2. Mega is 10 to the power of 6, and then I was going to multiply by the elementary charge, 1.6 times 10 to the power minus 19, and this thing here will give me around 240 picojoules, so 2.4 times 10 to the power minus 10 joules. It's not a super accurate reading of the graph, but it's clear that the correct answer has to be D because it is the closest value. Let's also have a look at some questions from Edexcel. Just a reminder that these are not official solutions, and if you spot a mistake, please do let me know. This is just my twist on the solutions. Okay, so first one, we've got a diverging lens. Which one of these is correct? So a diverging lens will always produce a virtual and an upright image. So correct answer is C. Question 2, when a sound wave passes from water into air, it slows down. Okay, whenever we have a sound wave or any wave changing substance, the frequency always remains constant. So I'm going to say that V is equal to F lambda. The frequency is constant. So if this has gone down, then the wavelength must have decreased as well. Correct answer is C. Question 3. Standard candles are used by astronomers to determine the distances to distant star clusters. They're known for their known luminosity. So these are very, very useful, but it's luminosity, which remember is the total radiated outward power from a star. Okay, the graph shows the variation of displacement with time for simple harmonic motion. Select the graph that correctly shows the variation of the velocity. Okay, so the thing to consider here, if you're not doing maths, is the gradient. So the velocity is the gradient of this graph. Because the gradient here is positive, I'm going to say positive m, meaning for positive gradient, the graph will start being from the positive region. So the correct answer is A. If you're doing maths, you can just think, okay, what type of a graph is this? It's a sine graph. The velocity is the derivative of the displacement. So the derivative of sine is just cos. Okay. Next one, 5. The graph shows the behavior of two materials which are placed under stress. We can conclude from the graph, so material X is stiffer. That is definitely true. We know that it's true because it has less of a strain for the same amount of stress. However, material Y has a stronger ultimate tensile strength. So material X is stiffer, but a small ultimate tensile strength, so therefore C is the correct answer, I'm pretty sure. Okay, next one. I really like this one. So you've got an HR diagram, clearly shows, choose the row that correctly identifies the relative ages of these star clusters. So we have to go from the youngest to the oldest. This one here is the only one that has white dwarfs, so probably a good way of answering this is to just think, okay, well, the white dwarfs are going to have to be the oldest stars, so I'm going to go for B being the correct answer. Why is a white dwarf always the oldest? Because it's the final stage of the life cycle of a star, and then they tend to have a huge lifetime afterwards. Okay, 7. A planet moves around the sun in a circular orbit of circumference 2 pi r. The work done in one orbit on the planet by the gravitational force is 0. Why is it 0? If you have a perfectly circular orbit, then the displacement is perpendicular to the force. Therefore, the work done is equal to Fx cos of 90 degrees, which is just 0 joules. Okay, question 8. We have a small sphere is falling through a liquid. The viscous drag force acting on the sphere will increase if the density of the liquid decreases. Nope, that will have the opposite effect. The radius of the sphere decreases. That will also have the opposite effect. Temperature of the liquid decreases. That sounds right. But let's just double check the next one. Viscosity of the liquid decreases. This is definitely wrong, so it's got to be C. Okay, number 9, we've got a converging lens is used as a magnifying glass. So, okay, choose the row that correctly identifies the nature of the image. We're given that an image is produced that is 30 centimeters away from the lens and is twice as big. So we can use the magnification equation that says that magnification is just equal to, I always forget this one, it's V over U, isn't it? Yep, V over U. So if the magnification is 2 and we are given the image distance, which is 30 centimeters, we can work out our object distance just by dividing those numbers. So it's going to be 30 divided by 2, which is what, 15 centimeters. This will be virtual because it will be on the same side, and therefore, so virtual image, it will appear to be there even though it's not actually there. 15 centimeters, correct answer is C. Okay, I think we've got just one more. Select the graph that shows correctly the relationship between the gravitational force between two masses and their separation r. Okay, well, we want a straight line through the origin typically in those, but let's say that F is equal to GMM over R squared. So if that's the case, if we were to plot a graph of F against 1 over R squared, we are going to get a straight line through the origin, because if this is on the y-axis, if this is on the x-axis, then my gradient will just be equal to this, where this M here is the gradient. I'll give it a little prime. Correct answer has got to be D. Okay guys, now hopefully this video was useful. I've also posted a really important video that you really need to see before the exams right over here.